Okay, so what we have here is a simple demonstration of amplitude modulation, and to do this I've set up a chip called the AD633 to do this process, and this is the circuit here. It's very simple, and it's just come directly from the data sheet for this chip. Now what you can see here is there's two signal generators, one producing a carrier frequency of around about 100 kHz and another signal generator which is just going to produce the lower frequency modulating signal. At the bottom we've just got a power supply. Now this is a digital signal oscilloscope, or a DSO, and this is capable of showing signals in both the time domain and the frequency domain. So currently you're actually seeing a time domain waveform of an unmodulated carrier. Now if I just adjust the time base a little bit, we can expand the time base a little bit, and we can see, if we zoom in, that we have indeed got a sinusoidal waveform there. And as I said before, it's got a frequency of around about 100 kHz. If I zoom out, changing the time base, it just looks like a continuous yellow band because the resolution of the DSO is not capable of resolving the waveform. Now it's currently unmodulated, so the amplitude of the modulating signal is set to 0. And if I just crank that up a little bit, we can see what happens. Okay, and we're starting to see some amplitude modulation there. Okay, that's the full extent to which I can increase the amplitude of the modulating signal. Now it's currently around about 1.5 kHz. So if I increase the frequency of the modulating signal, that's the signal that's producing this rather nice sinusoidal envelope here, we can see that those peaks are going to get closer together. Okay, so I've now cranked it up to around about 3 kHz, and we've got about twice as many peaks as we had before. And if I lower the frequency again, so all I'm doing here is just changing the frequency of the modulating signal. The carrier signal is remaining the same in frequency. Now I can actually change the type of signal that the modulating waveform generator is producing, and I could select, for example, square wave or triangular wave. And let's just have a go at that. So if I select square wave first of all, you can see that the signal is now AM modulated with a square wave, and now with a triangle wave. Okay, so we can see quite clearly what amplitude modulation represents here. The modulating waveform is currently set to about 3.5 kHz. Now on the screen of the DSO we can see both the time domain waveform, that's the yellow waveform at the top, and also the frequency domain waveform, and that's the purple waveform at the bottom. And that's exactly as we would expect for an AM modulated signal. We have a central carrier which has a frequency centered on 100 kHz and two sidebands. Now we would expect that as we change the frequency of the modulating waveform, that's the lower frequency, we would expect that the sidebands would move in and out. So what I'm going to do now is to increase the frequency of the modulating waveform. Okay, so if we take that up a bit, and if we now look at the sidebands, we can see that they're considerably further apart from the carrier than they were before. Now if I just do that, change the frequency while we're looking at the frequency domain waveform, I'm now going to lower the modulating frequency, and you can see the sidebands are moving in towards the carrier. And then if I increase the modulating frequency, the sidebands are moving away from the carrier. Now the DSO is currently set to have a frequency per division of about 2.5 kHz. So each of these main divisions on the screen that you can see in front of you, about a centimetre wide, are represent 2.5 kHz in terms of frequency. And the carrier is centered on approximately 100 kHz at the moment.